Welcome to the series of lectures on combinatorics. In this course, we will learn how to solve counting problems in daily life and natural sciences. In daily life, we face a lot of counting problems whose solutions are not easier. For example, if I am asked to solve the problem, how many ways are there to arrange 5 boys and 3 girls in a row such that no girls are adjacent? So think about the solution of this problem. The answer to this question cannot be given until we know about some basic terminologies about counting problems. There are many more such kind of problems in daily life which we face. So this course is all about such kind of problems as well as their solutions and their techniques. In this lecture, we will talk about two basic principles of counting. The first one is addition principle and the second one is multiplication principle. So we will define them one by one. This principle says that suppose there are either n1 ways or n2 ways to do a task, then there are total n1 plus n2 ways to do the same task, provided that there is no common way between n1 and n2. What is meant by this statement that there is no common way between n1 and n2? It means that if we have n1 ways to do some particular task and we have n2 ways to do the same task, such that in n1 ways there is no way which has been counted in n2. What does that mean? Let's understand this thing by the following example. Suppose one can reach city Q from city P by sea, air or road. Suppose there are 2 ways by sea, 3 ways by air and 5 ways by road. Then the total number of ways from city P to city Q are 2 plus 3 plus 5, which is 10, because these are the number of ways by sea, these are the number of ways by air, and these are the number of ways by road. You can see this is n1, this is n2, this is n3. You can see the definition of the addition principle. It says that there is no common way between n1 and n2, right? So you can see there is no common way between the ways from the air and between the ways from sea and between ways from the roads. You know, if we have a way which is from the sea, it cannot be from the road, it cannot be the same as from the air. So they are totally disjoint and different ways. Therefore, we had used the sum rule of counting or addition principle. Addition principle can also be described in set theory in this way. So let A1, A2 up to AK are finite sets which are pairwise disjoint. This means that AI intersection AJ is empty for all IJ. Then the number of elements in the union of all these sets, this means that this is the union of all these sets A1, A2 up to, and this absolute value means the number of elements. You can see it is explained here. This is the number of elements over the union of all these. You can see this is the union of A1, A2 up to AK, and this notation is for absolute value or the number of elements. So it says that the number of elements in the union is the same as the sum of number of elements in each set. What does that mean? Let me elaborate it. It means it is equal to the number of elements in the first set plus number of elements in the second set plus dot 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 plus the number of elements in the last set. So if you are going to count the number of elements in the union of those sets whose intersection is empty, if you have this condition here, you can see, then number of elements in the union is the same as the sum of all values, right? This is the set theoretic definition of addition principle. So look at the first example below. It says that find the number of ordered pairs xy such that x square plus y squares is less than or equal to 5. We will find the number of ordered pairs x, y belongs to set of integers. We need such integers such that the sum of their squares is either 5 or less than 5. Let us suppose that S is the set of those all ordered pairs such that x square plus y square is less than or equal to 5. I can write this set in this way as well. xy belongs to z such that x square plus y square is either 0 or 1 or 2 or 3 or 4 or 5. So we will make 6 different subsets of this set such that S0 contains those ordered pairs from Z such that x square plus y square is equal to 0, and S1 contains those ordered pairs such that x square plus y square is equal to 1. Similarly, S2, then S3, then S4, and then S5. So I've written down all of these sets. At the end, you can see that there is no common element in all of these sets. So I will find the cardinality of each set, and we will add their cardinalities according to the sum rule of counting of set theoretic shape. So first we find the cardinality of S0. You can see there is only one ordered pair in this set, which is 0, 0, such that 0 square plus 0 square is equal to 0. There is no other element in this set such that the square of both entries is equal to 0. So the cardinality of S0 is 1 because it contains only one point. So what about S1? You can see S1 contains those elements of those ordered pairs from Z such that the sum of their square is 1. You can see we have these elements 1 0 0 1 minus 1 0 0 minus 1. You can see these are all such ordered pairs which satisfy this condition, right? There is no other ordered pair which satisfy this condition. So the cardinality of S2 is 4 because we have only 4 elements which satisfy this condition. So the cardinality of S2 is 4. What about S3? Are there ordered pairs in Z such that the sum of their square is 3? The answer is no. there is no ordered pair in Z such that the sum of their squares is 3. So the cardinality of S3 is 0 because it is empty set. So I will write the cardinality of S3 is 0. So what about S4? S4 contains those ordered pairs such that the sum of their squares is 4. You can see these are only 4 elements, which are 2 0 0 2, and then minus 2 0 and 0 minus 2. So these are only 4 elements, 4 ordered pairs in Z. Sorry, this is not Z, this is Z cross Z. So the cardinality of S4 is 4. What about S5? S5 contains those ordered pairs in Z such that the sum of their squares is 5. You can see we have these number of elements 2 comma 1, then 2 comma minus 1. Then change their signs, minus 2 comma 1, minus 2 comma minus 1. Now change their positions. I have 1 comma 2, then 1 comma minus 2, then minus 1 comma 2, then minus 1 comma minus 2. Yeah. So we have 8 ordered pairs whose sum of squares is equal to 5. You can check there is no more ordered pair in Z cross Z which satisfy this condition. There are only 8. Since we have found all of these, you can see that in S0, S1, S2, S3, S4 or S5, there is no element common in all of these sets. Right? You can check. I have written down the elements before you. You can check there is no element which is common in any of these two sets. So by the sum rule of counting in set theoretic form, we have the sum of cardinalities of all these sets. Cardinality of S0, then S1, then S2, then S3, then S4, then the cardinality of S5. I have proved that the cardinality of S0 is 1, the cardinality of S1 is 4, the cardinality of S2 is not given here. Okay, let me find it. So in order to find the cardinality of S2, we will have the ordered pairs in Z cross Z such that the squares of their sum is 2. So we have such kind of ordered pairs 1 comma 1, 1 comma minus 1, then minus 1 comma 1, then minus 1 comma minus 1. Since we have only 4 ordered pairs in S2, so the cardinality of S2 is also 4. So now we have found all of these cardinalities. The cardinality of S0 is 1, the cardinality of S1 is 4, the cardinality of S2 is 4, this is 0, the cardinality of S3 is 0, the cardinality of S4 is 4, the cardinality of S5 is 8. After adding all of these terms, we will get 21. So this is only because of sum rule of counting or addition principle. In the next video, we will talk about product rule of counting or multiplication principle.